As you can see on the screen, today we're going to be talking about the addition rules for probability. These are the rules we use to answer or kinds of probability questions. Like, what's the probability of one thing or another thing being true? Let's start with an example. If you pick a card at random out of a deck of cards, what's the probability of getting a jack or a queen? Now, this is one question. It's not two separate questions. So imagine a situation where you're picking a card, and to win the game, you would win if that card was either a jack or a queen, but not if it was anything else. So we want to know, what are your chances of winning? What are the chances that that card you pick turns out to be either a jack or a queen? There are 52 cards in all. And out of those 52 cards, there are 4 jacks and 4 queens. So altogether, that's 8 possible outcomes where this happens, where the card you pick is a jack or a queen. So the probability is 8 over 52. And then you could reduce that to lowest terms, or you could divide and write it as a decimal or as a percent. But I'm not going to worry about that right now. I'm going to point out that the probability of getting a jack or a queen is just equal to the probability of getting a jack, 4 over 52, plus the probability of getting a queen, which is also 4 over 52. Next example. What's the probability of getting an ace or a spade? So there are 4 aces. There are 13 spades. If you add 4 plus 13, you get 17. So at first you might think 17 over 52? But wait, that's not right, because that would be counting the ace of spades twice. If you just go through and count out of all 52 possible outcomes, how many are there where this is true, where the card you picked is either an ace or a spade? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the probability that the card you pick is either an ace or a spade is 16 over 52. We could add together the probability of getting an ace, 4 over 52, plus the probability of getting a spade, 13 over 52, but then we would have to subtract off the one that got counted twice, because it was a member of both the aces and the spades. So these are examples of 2 different kinds of situations. In the first one, there was no overlap. Getting a jack, getting a queen, totally separate. They're what we call mutually exclusive. But getting an ace or getting a spade, there is some overlap there. Those are not mutually exclusive. So in that case, we couldn't just add the separate probabilities together. We had to account for the fact that something got counted twice. So when we talk about the probability of A or B, that means the probability that when you do the experiment, either A or B, or both, happens. The A and the B stand for whatever events you want to talk about happening, like getting an ace or getting a spade. And it matters whether the events are mutually exclusive. So mutually exclusive means that they can't both occur or both be true at the same time. They exclude one another. So if one of them is true, that excludes or rules out the other one. And it's mutual. It goes both ways. If either one of them happens, then the other one can't happen. So that's what it means to be mutually exclusive. Here are some examples of events that are mutually exclusive. Getting a heart and getting a black card when you pick a card out of a deck of cards. The card you pick might be a heart, or it might not. The card you pick might be a black card, or it might not, but it can't be both of those things at the same time. If it's a heart, it can't possibly be a black card, and if it's a black card, it can't possibly be a heart. Rolling a 1 and rolling an even number when you roll a die. Either one of those could be true, but they can't both be true at the same time. They're mutually exclusive. Rolling doubles and rolling 7 on a pair of dice. If the dice add up to 7, they can't be doubles. And if they're doubles, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, they can't add up to 7. A person chosen at random is a man, is a woman. Now here are some examples of events that are not mutually exclusive. That means that they could both be true at the same time. Getting a heart and getting an ace. If the card you happen to pick is the ace of hearts, those would both be true. Rolling a 1 and rolling an odd number. If the number you roll is a 1, then it also counts as an odd number. Rolling doubles and rolling a 10. If the dice come up 5, 5, that counts as doubles, and it also counts as rolling a 10. A person chosen at random is a woman, is married. If the person is a married woman, those are both true, so there is some overlap there. So the reason this matters is that we have two separate rules depending on whether we're talking about things that are mutually exclusive or not. So addition rule 1 is the one we can use if we know that we're dealing with things that are mutually exclusive. If events A and B are mutually exclusive, then the probability that A or B will occur, the probability of A or B, is equal to the probability of A plus the probability of B. So to answer the OR question, we just add together the individual probabilities. For example, let's say we have a bag of M&Ms with 3 green, 2 red, 5 yellow, and 10 brown. And that adds up to 20 in all. And we reach in and we choose one at random. What's the probability that it is red or green? So there's 2 red ones. We've got a 2 over 20 probability of getting a red M&M. There's 3 green M&Ms, so we've got a 3 over 20 probability of getting a green M&M. And those are mutually exclusive. The same M&M can't be both red and green at the same time. So we can just add those probabilities together and get 5 over 20 as the probability that the M&M we pick is either red or green. And that reduces to 1/4, or you could write it as a decimal as 0.25. But notice there's 5 of these M&Ms that fit the description of being either red or green out of 20 in all. Now, if we're talking about events that are not mutually exclusive, then we can't use addition rule 1. We can't just add the individual probabilities together and take that as the answer. In that case, we have addition rule 2 that says that the probability that A or B or both will occur, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. The reason this works is it's like we count up all the ways A could happen plus all the ways B could happen, but then we subtract the ways that we counted twice because they got counted in the A's and the B's. So by subtracting the probability of A and B, we make sure all the outcomes only get counted once each. For example, let's say a building has 2 restrooms. One's upstairs and one's downstairs. At any given time, there's a 0.60 probability that the one upstairs will be available, that there won't be somebody in it. And there's a 0.80 probability that the one downstairs will be available. And there's a 0.50 probability that both will be available, the one upstairs and the one downstairs. What is the chance that at least one of them is available? That is, what's the probability that the one upstairs is or that the one downstairs is available? Notice this is an or kind of question. So this is what we were just talking about. The probability of something or something else is equal to the probability of the first thing plus the probability of the second thing minus the probability of both of those things, A and B, both being true. So here the two things, the two events are the upstairs bathroom being true and the upstairs bathroom being available and the downstairs restroom being available. So according to that rule, we ought to take the probability of the upstairs being available plus the probability of the downstairs being available minus the probability of both being available. So that would be 0.60 plus 0.80 minus 0.50. And that comes out to be 0.90. So that's the answer to the question. There's a 0.90 probability, or a 90% chance, that the upstairs or the downstairs, or possibly both, would be available. I have one more multi-part example that I want to take you through, but it may take a while, so I'm going to make that a separate video. And in this video here, and then in part 2, we'll look at another example that involves OR kinds of questions.